Hello, my name is Alexander.
Hi, and my name is Nikita.
Hi, I'm David. This is our second assignment for first topic.
Disease models. We will now build a simple model of an infectious disease. Assume the total population we are studying is fixed at n individuals. This population is then divided in 3 separate pieces. The first piece that are susceptible to becoming infected are called susceptible. Second one that can infect others, they are called infectious. And third group that have been removed from general population. These are called removed, and their number at time is labeled by R. Individuals stop being infectious at positive rate gamma, which is proportional to the number of individuals that are in the infectious pool. More or less, if an individual stops being infectious, that means that this individual has been removed from the population. This could mean only that they have died. That means that the infection has progressed to the point where they can no longer pass the infection to others, or they have been put into quarantine in a hospital. Susceptible individuals are those capable of catching infection. So, we assume the rate of change of susceptibles is proportional to this interaction with positive proportionally constant. So mathematically, we assume that S prime equals R as I. We can then figure out the net rates of changes of the 3 populations. The infectious population gains at the rate RSI and loses at the rate gamma I. So that I prime equals RSI minus gamma I. The net change of susceptibles is that of simple decay. Susceptibles are lost at the rate RSI, so thus we have S prime equals minus RSI. Finally, the removed population increases at the same rate the infectious population decreases. So we have R prime equals gamma I. And all in all, our complete infectious disease model is 4 equations that we can get here. Disease model nucleins. When we set I prime and S prime to 0, we obtain the usual nuclein equations. We see I prime equals 0 when I equals 0, or when S equals gamma divided by R. This nuclein divides the IS plane into the regions shown on the graph. The equation for our system is I prime equals I multiplied with the gamma S minus R. Setting this to 0, we get I equals 0 and S equals gamma R, whose graphs are shown. We show the algebraic sign of I prime in all regions determined by these 2 lines. Only quadrant I is relevant. Consider a trajectory that starts at the point of the positive I-axis. Hence, I0 more than a 0 and S0 equals 0, it is easy to see that if we choose ST equals 0 for all time t and I satisfying, I prime equals minus gamma I. The S prime equation for our system is S prime equals minus IS. Setting this to 0, we get S0 and I0, whose graphs are shown. The algebraic sign of S prime divides the IS plane into the regions shown. The S prime equals 0 and I prime equals 0 equations determine regions in the IS plane with defined algebraic signs for derivatives.
I versus S curve.
Comparing I and S curve, we can get this equation, which can be further simplified. A plausible trajectory starting at the point S0 more than gamma divided by R and I0 more than 0. Another trajectory starting at S1 less than 0 divided by R and I0 0 more than 0. It is also shown. In addition, the intersections with S-axis are labeled S infinity 0 and S infinity 1 respectively. It is clear that this curve has a maximum at the critical value gamma divided by R. Gamma divided by R is called in disease modeling susceptible rate ρ. Summarizing all said before, we go to conclusion that when S0 exceeds the critical infectious to susceptible ratio ρ, because of the number of infectious increases to its maximum before it begins to drop. This behavior is easily interpreted as infection going out of control, or it has entered on epidemic phase.
During an epidemic, it's impossible to accurately determine the number of newly infected people each day or week. This is because infectious people are only recognized and removed from circulation if they seek medical attention. Indeed, we only see data on the number of people admitted to hospitals each day or week. That is, we have data on the number of newly removed people, which is an estimate of R prime. So to compare the result predicted by the model to data from real epidemics, we must find R prime as a function of time t. Further, we know ds divided by dr equals minus rsy divided by minus gamma y, and that equals minus s divided by rho. This equation we can solve to obtain s from r. Hence, we got the following equation. This equation is not solvable directly, so we will try some estimates. If a function f is differentiable, we know that we can approximate its value at the point x0 by its tangent line t. We have the following equation, where the tangent line t is the function, and the term et represents the error between the true function value f from x and the tangent line value t from x. That is, we got at equals f from x minus t from x. Another way to look at this is that the tangent line is the best straight line or linear approximation to f at the point x0. We all know from our first calculus course how these pictures look. If the function f is curved near x0, then the tangent line is not a very good approximation to f at x0 unless x is very close to x0. In fact, we can prove that f is twice differentiable in the following equation, where yt is some point between x and x0. We could ask what quadratic function q fits f best near x0. In a more advanced class, if f is 2 times differentiable, we could show that the best quadratic function is given by this equation. The new error is called EQ and is given by EQ equals f from x minus q from x. If f is 3 times differentiable, we can prove that in this equation, where yq is some point between x and x0. So if f looks like a quadratic locally near x0, then q and f match nicely and the error is pretty small. On the other hand, if f is not a quadratic at all near x0, the error will be large. Let's apply these ideas to this function. It is 3 times differentiable, so we can find the first order approximation and the second order approximation near the point r.
Rt and Rq are both values between r and 0. However, the largest error can be is 1, so we have the following estimates. So that for this function the actual values of Rt and Rq are not important towards estimating the error.
To estimate the solution of previous equation, we would like to replace the term e, which makes our integration untenable, with a quadratic approximation. We will approximate around the point r, which equals 0, and we have this equation. With a tangent error, we'll have this solution. Then we need to see if this error is not too large. Recall the I and S solution satisfies. An epidemic would start with the number of removed individuals R0 being 0. Hence, we know initially n is equal I0 plus S0, and so since R is equal n minus I minus S, and we'll have this equation. After some of simplification and taking into account constants, we can write our equation as simpler form. So let's go through some very important definitions in math and in our sphere. First one is hyperbolic functions. The main hyperbolic functions of the real number x are defined to be: first one, the hyperbolic sine, second is the hyperbolic cosine, third one is the hyperbolic tangent, and last but not the least is the hyperbolic secant. It is straightforward to calculate that the hyperbolic cosine in power of 2 of x minus the hyperbolic sine in power of 2 of x is equal 0. The same thing we can do if we take into account the hyperbolic tangent and the hyperbolic secant. Note that these definitions are similar but different from the ones you are used to with the standard trigonometric functions sinus, cosine, and so forth. So now let's go through the second definition, which is hyperbolic function derivatives. The hyperbolic functions are continuous and differentiable for all real x. So we'll have the hyperbolic sine x prime is equal the hyperbolic cosine x. The hyperbolic cosine x prime is equal to hyperbolic sine of x. And the hyperbolic tangent of x prime is equal to hyperbolic secant in power of 2 of x. Just like in trigonometric functions with inverse tangent, there is an inverse for the hyperbolic tangent also. Now we are going through third definition, is inverse hyperbolic function. It is straightforward to see that the hyperbolic tangent of x is always increasing, and hence it has a nicely defined inverse function. We call this inverse the inverse hyperbolic tangent function and denote it by the symbol the hyperbolic tangent if power of -1 x. So now, using our new definitions and some calculations formula, we can have this data to calculate the critical value ρ. How you can see, ρ in power of 2 is equal to half s0 divided by n minus s0, a big divided by a small in power of 2, and then 1 minus the hyperbolic tangent of power of 2b. It is a lot of work to generate the approximate value of r prime, but the payoff is that we obtain an estimate of the y divided by r ratio, which determines whether we have an epidemic or not. Thank you a lot for your attention.